Hello and welcome to the third integral of the day video. And it's been almost a year since I've done these, so I've not really been consistent at all. But regardless, the integral that we're solving today is the integral of arcsine of the square root of x. And like our previous videos, it looks pretty simple, but of course it's a very intricate and requires a lot of integration techniques as well. So at first glance, the only thing that looks like we can do is, for example, u sub the square root of x, right? Because there's nothing else we can really do. So let's just take, let's just call this something. I'll just call it y because we're going to need u later on. Say y equals root x, right? So when we differentiate that, we just get dy equals 1 over 2 root x dx, right? So, and then we also notice that y is actually equal to root x, so we can just plug that into here. So it just becomes dy equals 1 over 2y dx. So rearranging that to make dx subject to the formula, just get dx equals 2y dy. Okay. So now what we can do is, again, of course, plug this for dx into dx. Just rewrite this, and we get arcsine of y into 2y dy. Okay, so again, this is pretty similar to the first one, except now we can't use sub again, but what we can do is use integration by parts, right? And if you do or don't know what that is, essentially, integration by parts is when you have two expressions that are multiplied with each other, and you want to integrate that entire expression. So it can be represented like this. So just say u dv equals uv minus v du, right? So our u in this case would be arcsine y. Just write that down here. So arcsine y is our u. So when we differentiate this, we get du equals 1 over 1 minus y squared. And this is a standard derivative. So just something that you know by heart. And on the other hand, our dv is just 2y. So when we integrate this, our v just becomes y squared, because of course the integral of y is just y squared over 2. The 2's cancel out, so this is what we end up with. So we can just just plug these in back here. So just start doing the integration by parts. I'm just gonna box this off. Okay. So now when we integrate this, we get of course, we need uv. Our u is arcsine y, and our v is y squared. So this becomes y squared arcsine y. And then integral of v du. Our v is y squared again, and our du is this right here. So we just plug that in, and we get v squared by root of 1 minus v squared by dy, right? Okay. So if you look at this, it looks pretty similar to the integral of arcsine y, but of course we can't ignore this y squared above here. So the only option that we have now is to use trig substitution, and the reason I say that is because if you look at the square root over here, it says it has 1 minus y squared, and that looks pretty similar to a 1 minus cos squared theta or 1 minus sine squared theta, right? So we can just substitute y for either cos or sine theta and just see where that takes us. So I'm just gonna rewrite this down here. Okay, so just 1 second. Okay, so let's just take y as cos theta. Okay, so that will mean that when we differentiate this, dy is just negative sine theta d theta. Okay. And let's just ignore this part here because we already figured it out. So this is what we still have to work with, right? So let's plug these trig subs into this expression, into the integral. So what we end up with is just cos squared theta by the square root of 1 minus cos squared theta. And then you have to, of course, plug in dy. And this just becomes sine theta d theta. Okay. And as we already know, this expression over here is just equal to sine squared theta. And then that's under a square root. So that just becomes sine theta, right? So I'm going to rewrite this. This becomes cos squared theta by sine theta into negative sine theta d theta, right? And of course, you can cancel out the signs, and the final integral that you end up with is the integral of negative cos squared theta d theta, right? And if you notice the original integration by parts that we did, there's actually a negative sign outside the integral, and then now there's one inside, so both of them cancel out and you just end up with a plus. So I'm just going to rewrite the entire integration by parts with this new trig sub, and what we end up with is just y squared arc sine y plus the integral of cos squared theta. Okay. So again, this looks pretty similar, and if you do or don't already know how to integrate cos squared theta, it's pretty simple. So if there's a trig integral, there's a trig identity, which is essentially it's called a double angle identity, which is cos 2 theta equals 2 cos squared theta minus 1. And we can just rearrange this to make this the subject of the formula. And this becomes cos 2 theta equals cos 2 theta plus 1 over 2. So when we plug this back into here, it makes it much simpler for us to integrate this, right? So let's just rewrite this again. This becomes y squared arcsin theta, and then this just becomes half of the integral of cos 2 theta plus 1, right? So we can just split this into two integrals. So what we end up with is basically y squared arcsin. I'm just going to keep rewriting this first part. So this just becomes, and then plus. Okay, so all we have to do now is integrate both of these, right? And this one is this one's pretty simple. Let's just ignore this again. Just worry about this. So this one is pretty simple. It's just half theta, right? But for this one, let me just write that here. But for this one, of course, again, it's pretty simple, and you just need very simple u substitution. So for example, let's just take u as 2 theta, because we just want to get that into one, like cos x or cos t or something like that, right? So u is 2 theta. So that would mean that du equals 2 dx. So that means dx is just du over 2. And we just plug that back into this. So this just becomes the integral of, half times the integral of cos of u du over 2. And when we integrate that, this just becomes, okay. So the entire expression just becomes 1 over 4 sine 2 theta plus half theta plus c. Okay, so let me just rewrite this part down here as well. Let's erase this. So this just, so the entire integral is y squared arcsin y plus this. Okay, so now we notice that, of course, our original question was in terms of x, but now we just have an expression that's in terms of y and theta. So we have to get everything back to x, right? So first, let's get these two terms which are in theta. Let's just get them back to y. So up here somewhere, we said that y equals cos theta, right? So we can just go off that and convert these thetas to y's. So if y equals cos theta, so that would mean that theta is just arc cos of y, right? So we can just plug that into here, and as for and as for the sine 2 theta, we just use the double angle identity again, where sine 2 theta equals 2 cos theta sine theta, right? Okay, so just gonna again worry about this part only. So this just becomes 2 over 4 sine theta cos theta, and then this just becomes half arc cos y plus c. So again, cos theta is just directly y, because that's what we substituted in the first place. And as for sine theta, what you can do in this case is, what we can do in this case is just draw a triangle, as so. And let's just say this is theta, right? So if cos theta equals y, so that means the adjacent side has to be y and the hypotenuse has to be 1. So cos theta is y over 1, right? So for the same triangle, if we had to figure out what sine theta is, we just need this side, right? And we can just use Pythagoras' theorem. We get 1 minus y squared. So if sine theta is just the square root of 1 minus y squared, right? Okay. So just plug these into this expression here. And the total expression, including this part, comes to y squared arcsin y, and then plus 1 over 2, 1 over 2, and then cos is y, cos theta is y times root of 1 minus y squared. Then finally this part is just half of arc cos of y plus c. So we have one final step now, which is to get this entire expression, or entire antiderivative, in terms of x, because that's what our original question was in. And if we look somewhere up here, we said that y equals the square root of x. So we can just use that back down here and then just get it back. So let's write it back here, y equals square root of x. Okay. So just plug this in every y we see here. And this just becomes the square of the square root of x is just y, right? It's just x, my bad. So it becomes x times arcsin root x, right? And this is just half into root x, and then the square of root x is just x, so half into root x times the root of 1 minus x. And then this just becomes half, sorry, that looks pretty bad. So this just becomes half arc cos root x plus c. And that is, let me just rewrite this to make it look slightly better. So x arcsin root x plus half root x times 1 minus x plus half arc cos root x plus c. So this is our final antiderivative. And there's actually two answers, two antiderivatives that you can arrive at. And the reason for that is we actually, in the trig sub, we actually took y as cos of theta, but you can also take y as sine of theta, and you'd arrive at a different answer. But that would be correct as well, because the only difference between this expression here and that expression would be a vertical translation by a certain number of units, and that's where this concept of integration comes in. So any answer is correct as long as it's just a vertical translation of one another. So that or this would be correct, but this is what we finally arrive at.